Hello everybody! Welcome back to another Gregorius Maths video. In this video, I'm just going to be continuing my learning algebraic geometry series last time we looked at complex algebraic curves, and this time we look at complex projective curves. In order to motivate this a little bit, we might as well take a look at why we even study, because the algebraic curves thing, that was quite natural to study, but complex projective curves might seem a little bit more random. But to provide a little bit more motivation, you might have heard that hold on, let me just turn on a light. You might have heard that the projective plane is kind of like adding points at infinity, or maybe something like that, but we'll look at precisely what they are, what complex projective plane actually is, but for now, let's just have a little bit of motivation. So if we have y squared equals x squared minus 1, so something like that, and we have y equals plus or minus x. So actually no, hold on, let's just take a look at y equals cx for the moment. So these two curves, they intersect at 2 points, unless y at c is equal to plus or minus 1. So what happens when we have plus or minus x is something like this. Is basically these two curves are never intersect, but they are asymptotic as x and y go to infinity, and so they should kind of intersect at points at infinity. And so this type of phenomenon is what motivates the study of projective curves and so forth. And so today we're going to be making this precise. So first we might as well define the projective plane. Of course, this definition can be generalized for Pn, but today we're only going to be looking at P2. So we'll just denote it by, I'll try doing the math BB font for the P. Also, you might note that I have denoted it like this before, because we're obviously working with the complex projective plane and not any other projective plane. I'm just going to denote it as P2. What it is it's the set of all equivalence classes P x, y, z, such that x, y, z is part of, it's part of C3, i.e. x, y, and z are all complex numbers, but they're not all 0, i.e. it's not 0, 0, 0. And these equivalence classes, we have x, y, z being equivalent to w, v, u, for example, if and only if x is equal to some lambda w, y is equal to some lambda v, and z is equal to lambda u. For, of course, and this lambda can be a complex number as long as it's not 0. Okay, so these are our equivalence classes that we're working with, and that's what that is. And so we're going to be taking a look at complex projective curves now. So, of course, recall that a curve P of x, y, z is homogeneous of degree d if P of lambda x, lambda y, lambda z is equal to lambda to the d times p of x y z. And also note that the partial derivatives are all homogeneous of degree d minus 1. But of course, so with this definition, note this, and this is for all complex lambda. And so with this definition in hand, if we have a homogeneous curve of degree d, then a complex projective curve is defined as set of all of these equivalence classes such that p of x, y, z is equal to 0. Right, and now this is all well defined because, of course, for any representative by the homogeneousness of this curve, it's all equivalent. So yeah, no matter what choice we pick, this part is always going to be 0, so it's all good. And the degree of this curve, if we call it c, the degree of c is just this d right here. So okay, that all works out very nicely. And just a warning, this stuff might all feel quite familiar from last video. I'm just going through some basic definitions, basically the corresponding definitions for projective curves that I did in the last video. So for example, singular points and stuff like that. So, and yeah, I think we are ready to move on to singular points. So, if we're given a complex projective curve C, then and a point ABC on it, then the point ABC is singular if, and what we have is, of course, partial derivative of p at x, the partial derivative of p with respect to x at ABC is equal to the partial derivative of p with respect to y, and of course p is just this our curve which we're working with. So is equal to the partial derivative of p with respect to y. ABC is equal to the derivative of p at z. ABC is equal to 0. So, for example, and of course, a curve is non-singular if it has no singular points. So, for example, the curve y squared plus x squared equals z squared is non-singular. Because, okay, let's rearrange this. So, x squared plus y squared minus z squared equals 0, right? If we take the problem here is, of course, the definition requires that it's that this triple here is not 0, 0, 0. So when we take all of our partial derivatives, we're going to get 2x, 2y, and 2z. And these are only going to be equal to 0 when all of these three are 0, but of course we're not allowed to have that, so it's non-singular. Okay. But an example of a singular curve would be, for example, y squared z equals x cubed, we'll say. That is singular because at the point 0, 0, 1, at 0, 0, 1. Because if we take the partial derivative with respect to y, then we get 0. Take the partial derivative with respect to x, we get 0. take the partial derivative with respect to z, and again we'll get 0. I believe, yeah. Yeah. Hold on. Ah, yes, because this y squared will be preserved. Yeah, okay, yeah, it makes sense, yeah. It will be 0. Okay, good. I just had to think about that for a second. So, those are singular points, and of course they work slightly differently to the singular points that we had last time, but the definition is essentially the same. We just have to work with different rules, slightly. So, it is a bit tricky, but, you know, that's the nature of these types of things. So just a couple more definitions, and then in the next video we'll go over kind of affine and projective curves, so we'll go into more depth on these definitions next video. I just need to get them out of the way. So a projective line is defined as alpha x plus, and it is typical definition you would expect, alpha x plus beta y plus, I don't know, some gamma z equal to 0. That's for complex alpha, beta and gamma not equal to 0. This is a projective line, and again the tangent line at a point ABC is defined exactly the same way as last time. If we're given a point ABC, the tangent line is partial derivative of RP with respect to x at ABC x plus partial derivative of P with respect to y at ABC y plus the partial derivative of P with respect to z at ABC z. And yeah, I think that's about all I wanted to cover, really. That's most of the relevant stuff. An interesting side note, but I don't think this will, unless I'm wrong, I mean it might be relevant later, but I don't see this being relevant later in the series, but you know, interesting side note is that our curve C, so if we just go back here and we call this curve C, our curve C inherits the topology from our projective plane here, just as a subset of the projective plane. And of course C is Hausdorff because it's a subset of a Hausdorff space, and it's compact. It's compact because polynomials are continuous, and so quickly we find that it's compact basically, using the definition being closed bounded subset of complex plane. So just an interesting note, we do inherit a topology on this curve just from being a subset of the projective plane, and every single curve is Hausdorff and compact. But yeah, that's all I really wanted to say. I mean, it might not have been the most exciting of videos, but it's good to get these definitions out of the way now and do interesting stuff with them later on in the series. Apologies about a slightly delayed upload. Of course, nothing to the extent of what I had done recently, but I was in Belgrade, so obviously I could not record the video there. But yeah, that's my excuse that time. I actually do have an excuse. But anyway, I will see you guys in the next video, which should actually be quite an interesting one. Not just going through definitions and a couple of examples. And then actually there's a bunch of exercises in this book, so what I am going to do is I'm going to do another video after that, after the next one, not just going through what I learned, but actually going through exercises that I've done. So, anyway, yeah, that's tons of waffling. So, yeah. Bye.